Okay, in this lecture we're going to begin our section 6.3 material on step functions. And we'll see that step functions are very useful in solving differential equations that might involve a discontinuous forcing function. And these step functions have some really nice properties when it comes to the Laplace transform. So let's start with a definition of the unit step function, or sometimes called the Heaviside function. And it's the function defined as follows. So let me start with notation. We denote the unit step function as u subscript c of t, and this is the notation used in the Boyce and DePrima textbook, which is what my notes follow. I'll mention for some other textbooks, you'll see the notation u of t minus c for this function, or sometimes h of t minus c, h for Heaviside instead of unit function. So any of these notations can be used. These are the common notations for this unit step function. And let's see how it's defined. So it is defined as 0 for all t less than c, and 1 for all t greater than or equal to c. So at the time c, we have a jump discontinuity, or a step, of 1 unit, hence the unit step function. Now for our course, since the Laplace transform involves values of t which are non-negative, we are only going to be interested in values of c which are non-negative. Now to better understand or help visualize this unit step function, let's consider its graph. Here I mentioned the graph of y equals u sub c of t is shown below. So let's look at it here. We have in the ty plane the graph of y equals u sub c of t, and it's the function which is defined as 0 for all values of t up until the time t equals c, at which point the value of our function jumps up to 1 and is defined as a constant 1 for all time greater than or equal to c. And then I mention as a note that this function could be scaled so that our jump corresponds to, or our step corresponds to, not just a value of 1. So for instance, if we were to consider in the ty plane the graph of some constant, let's say k times this unit step function, that would be the function defined as 0 up until time c, at which point our unit function u has a value of 1, and since I'm multiplying by k, the value would be k times 1 for all time greater than or equal to c. So we can scale the size of this step. Or we could also consider having a negative step. For instance, if we considered in our ty plane the graph of, let's say, k minus u sub c of t, we would have the function whose initial value for all t less than c is the constant k, up until we hit time c, at which point the value of our unit function becomes 1, and y would be given by k minus 1 for all t greater than or equal to c. So we can scale this unit function by multiplying by a positive or negative constant to scale the size of our step, including a step in the negative direction. So let's look at some examples to help familiarize ourselves with this unit step function. In this first one, we are asked to sketch the graph of f of t, which is equal to u sub pi minus u sub 2 pi. So here, each of these unit functions is either valued as 0 or 1. And we have jumps, or steps, occurring at time pi and time 2 pi. So let's start by writing out the definition of this function, f of t, as a piecewise-defined function. And since we have steps occurring at time pi or 2 pi, I can think about my function being defined on the intervals from 0 up until time pi, where I have my first jump, from time pi up to 2 pi, where my second jump occurs, or all time greater than or equal to 2 pi. And let's think about how our function is defined on each of these intervals. So on the interval from 0 to pi, neither one of these unit functions has made its turn on from a value of 0 to 1. So we would have 0 minus 0. On the interval from pi to 2 pi, the first unit function has turned on. It's jumped from 0 to 1, and then I'm subtracting the second unit function, which has not yet turned on. So I would have 1 minus 0, or 1. And for all time greater than or equal to 2 pi, both of these unit functions have made their jump from 0 to 1. So I would have 1 minus 1, which takes me back to 0. So my graph here in the ty plane, starting at time 0, our function has a value of 0 until time pi, at which point the value of our function becomes 1. And it remains 1 until time 2 pi, at which point we jump back down to a value of 0, and it's defined as 0 for all t greater than or equal to 2 pi. So let's look at another one. In the next example, we have the same sort of problem. We are asked to sketch the graph of this function, f of t, which is t minus 3 times u sub 2 minus t minus 2 times u sub 3. So when I look at this one, I see that I have a function involving a unit step function at time 2 and time 3. So if I think about the piecewise definition of this function, its domain is divided as follows. We have all of the times less than time 2, where the first jump occurs, values of t which are greater than or equal to 2, but less than 3, where the second jump occurs, or times greater than or equal to 3. And let's think about how my function is defined on each of these intervals. So on my first interval from 0 to 2, Both of these unit functions have not yet turned on. They're both valued as 0. So I have 0 minus 0. On the interval from 2 to 3, my first unit function, u2, has turned on to a value of 1, but the second function, u sub 3, is valued as 0. So f is then t minus 3 times 1 minus 0, which leaves me with just t minus 3. And for time greater than or equal to 3, both of these unit functions have turned on. They're valued as 1. So I would have t minus 3 minus t minus 2. So the t's cancel. I'm left with negative 3 minus a negative 2, or plus 2, which leaves me with a value of 1. And so let's look at our graph of this function in the ty plane. We have a function whose starting value is 0 at time 0. And it remains valued as 0 up until time 2, at which point we change definitions. At time 2, my function becomes defined as t minus 3. So if t is equal to 2, the value of my function becomes 2 minus 3, or a negative 1. And then as t increases to 3, t minus 3 increases linearly towards a value of 0. So here our graph on this interval from 2 to 3 is a line segment of slope 1. And then at time 3, the value of my function jumps back to a negative 1 and is defined as negative 1 for all t greater than or equal to 3. So here we've defined our unit step function and had a little practice with graphing functions involving this unit step function. So let's look at some other examples working in the opposite direction. One nice property or one nice application of these step functions is that any piecewise defined function can be written in terms of a unit step function. So let's look at that here. In this first example, we are asked to sketch the graph of the function f of t, which is defined piecewise as 0, 2, or negative 2 on different intervals. And then we're asked to express this function in terms of the unit step function, u sub c of t. So let's start with our graph of this function in the ty plane. So here we have a function whose initial value on the first interval is 0, starting from time 0 until time 3, at which point a jump occurs, or a step occurs, and the value of our function f of t becomes 2. And then it remains valued as 2 until time 5, at which point a jump occurs and the value of our function changes to negative 2. And then it remains valued as negative 2 for all t greater than or equal to 5. So we have our graph, and now let's look at how to express this function in terms of a unit step function. So this function f of t starts with a value of 0. And then at time 3, a jump occurs. So to indicate that jump or that step, I'm going to take a unit function at the time where the jump occurs, time 3, and multiply by the value that I want my function to take. Here we had a jump upward from 0 to 2. So I would multiply by 2. And then at time 5, we had another jump or a change in our definition. So let me add at time 5 a unit step function. And the jump that occurred was from positive 2 to negative 2, a jump of 4 units downward. So let me multiply that unit function by the size of the jump that occurred, negative 4. And we have f of t is 2 times u sub 3 minus 4 times u sub 5. So let's look at another one. In the next problem, we have the same sort of question. We're asked to sketch the graph of this piecewise defined function f of t, and then express that function in terms of the unit step function. So again, let's start with the graph here. In our ty plane, we have a function whose initial value at time 0 is 1, and it remains valued as 1 until we hit time 1, at which point a jump occurs where the value of our function becomes a negative 1, and it's defined as negative 1 until time 2, at which point the value of our function becomes 2, and it's defined as the constant 2 until we hit time 3, at which point our function jumps back down to a value of 1, and then is defined as 1 for all time greater than or equal to 3. So for this function, f of t, let's express this in terms of a unit step function. So for f of t, we're going to start with how our function was defined on its initial interval. So on the interval from 0 to 1, we started with f of t as 1. And then at time 1, a jump occurred. The size of this jump, or this step, was 2 units downward, from positive 1 to negative 1. So I could subtract 2 times u sub 1 of t. And then at time 2, another jump occurs, or another step, and the size of this step from negative 1 to positive 2 was 3 units. So I could add a step of 3 units upward at time 2. And then at time 3, we had a unit step of negative 1. So I could subtract 1 times a unit function at time 3. So here we have described these functions f of t, which are piecewise defined, in terms of this unit step function. Now in these two examples, our functions f of t were defined as constants over different time intervals, but that may not always be the case. So let's look at some more general examples. Here we have the same sort of question, but a little more complex. We're asked to sketch the graph of these functions and then express the function in terms of the unit step function, u sub c. So in our first example, we have f of t, which is defined as t squared on the interval from 0 to 2, and 1 for all time greater than or equal to 2. So let's start with our graph here. In the ty plane, we have a function whose starting value at time 0 is t squared on the interval from 0 to 2. So we know the graph of t squared is a parabola opening upward with vertex at the origin. And at time 2, the value of our function would be approaching 4. And then at time 2, a change in definition or a jump occurs, at which point the value of our function becomes 1. And then it remains defined as 1 for all time greater than or equal to 2. So now let's try to express this function f of t in terms of a unit step function. So in a similar way to what we saw previously, we would start by defining f of t as its definition on the first interval. Here from 0 to 2, it's defined as t squared. And then our change in definition occurs at time 2. So to denote this jump or change in definition at time 2, I'm going to add a unit step function at time 2. And then I'm going to multiply that step function by the definition that I want my function to have on this next interval, or the value I want it to have on my next interval, which would be a value of 1. And then I need to kill off the t squared that was appearing on the previous interval. So I could subtract that value of t squared starting at time 2. So we have the following. So let's look at another example of this. In the next example, we are asked to sketch the graph of this function and express it in terms of the unit step function. So let's take a look at our graph first. Here in our ty plane, we have a function that is defined as t on the interval from 0 to 2. So starting at time 0, the value is 0. And then as t increases to 2, the value of our function increases linearly with slope 1, y equals t, towards a value of y equals 2. And then for time between 2 and 5, our function is valued as a constant 2. And then at time 5, we change the definition of our function to 7 minus t. So when t is equal to 5, we have 7 minus 5, or 2. And then our function is valued as 7 minus t, so it decreases linearly until we get to t equals 7. So our function is decreasing with slope 1 towards a value of 7. And then for all time greater than or equal to 7, our function remains valued as 0. So we have the graph of our function shown here. And to express this in terms of the unit step function, let's take a look at it. We're going to take f of t as t on our initial interval from 0 to 2. And then starting at time 2, we change our definition. So I'm going to add a step function at time 2. And I'm going to take the value that I want my function to have on the next interval, which would be 2. And I have to subtract its definition on the previous interval, which was t. And then we have another jump occurring at time 5. So I would multiply by a unit function, or add a unit function at time 5. And multiply that unit function by the value that I want my function to take on the next interval, which would be 7 minus t. And then I have to subtract the value that the function took on the previous interval, which was a constant 2. And then we have one more jump occurring at time 7, so I could add a unit function at time 7 times the value that I want my function to take on the next interval, which is 0, minus the value of the function on the previous interval, which was 7 minus t. And so simplifying this a little bit, we have t plus u2 of t times 2 minus t plus u5 of t times 5 minus t plus u7 of t times negative 7 minus t, or t minus 7. So of course this process can be generalized to any piecewise defined function, and we see that we can express any piecewise function in terms of this unit step function.